Okay, so this is the Holtz method or double exponential smoothing. I'm just going to set, this is going to be set up like figure 9.14 on page 339. So to do that, we've just actually got to add some additional rows. So this actually starts on row 7, give one more row. And I'll just call this or Holtz. I generally call it Holtz method. Um, Now we've got two parameters. We've got the alpha, which is the same as the exponential smoothing for how quickly we update the level, and we have the beta for how quickly we update the trend. Again, at the end of this, I'm going to show you how to optimize this using Solver, which the book doesn't do. And in the example, um, we only kind of have the first kind of 10 values. So let's just remove anything below that. Just make sure I've not left anything. And the years are actually, rather than the actual year, we have years 1 to 10, and then we actually have a prediction for year 11. And we have the level, the trend, the forecast, and the absolute error. And let's just Arial 12 it. What happened to my Arial? Okay. Let's just spread this out a little bit. So the idea is we're building up our forecasts over time. And the first thing we need to do is we need to kind of initialize our kind of forecasting. So the first level is just going to be, and we can't, because we have to calculate an initial trend, we can't really make a forecast until period 3. So my first level is just going to be the level, the actual value. And the second level is going to be the second value. We're not going to start forecasting until period 3. And the first trend is the same for each thing. It's just going to be C9 minus C8. C9 minus C8, and we're not making any forecasts. This just sets us up with our level and initial trend. So the next level, and this is the equations on page 338, but it's actually a little bit unclear that we're basically taking alpha times, it's similar to exponential smoothing, we're taking alpha times the forecast plus 1 minus alpha our previous forecast, which is the previous level plus the trend. So it's going to be alpha times our actual value plus 1 minus alpha, 1 minus B4, times the previous level plus trend. And that gets us 426 million. Let's just make sure that all of these values format cells. We're numbers, we're not bothering with decimal places, and we're using the 1000 separator. Okay. And obviously, we don't want to, we're going to be dragging down and we don't want the B4 to move. So we're just going to do that. We're not going to be dragging across on this one, so we don't need to dollar anything else for the moment. But that just means we can drag down. And the trend, this is just going to be beta times the latest trend from the data, and the latest trend from the data is just going to be the difference between the levels. This is why it's sometimes called double exponential smoothing. We're doing this smoothing twice. So this is just this one minus this one plus 1 minus beta times the previous trend, which is this one here. And we get minus 6 million. Okay, so that's good. And each of the forecasts is just going to be the previous level plus the trend. There we go, just checking I'm agreeing with the spreadsheets. And the absolute error is just as we've defined it before. It's our actual value minus the forecast. So for no fault of our own, before any real updating, we have like a pretty bad initial forecast. Okay, just do a check. Okay, so the betas need to actually be dollarized as well, so when we don't lose the beta as we drag down. So let's just have a final check. Our level is the current value times alpha, sorry, plus 1 minus alpha times the forecast, which is actually the level plus the trend. And our trend is beta times the current difference in levels, which is kind of like our new trend, and 1 minus beta for our previous trend, which is D9. The forecast is the previous level plus the trend, which in this case, we're going to have this error pretty much whatever. And the error is the actual minus the forecast. Okay, I think we can drop down now. Okay, perfect. And we can actually do, since the forecasts are from the previous row, we can actually do one more forecast. Okay, so we basically, this is our exponential smoothing. Now, we're just going to do the mean absolute deviation. I'm going to try and keep relatively consistent with the book. And the mean absolute deviation here is just the mean value of these values. So it's just going to be average. And just one extra thing we need to do, we calculated the error for all of these, but we actually, my column says absolute error. So I'm just going to make this the absolute error. I'm going to drop it down so you see all these errors now are absolute. And the mean absolute deviation is just the average of all of these errors. Very simple. And voila. Now, my mean absolute value deviation is approximately 26 million. This is just how goes the yearly coal production. So let's find alphas and betas to actually minimize this to get the best possible forecast. So let's go to data, go to solver, and we're going to minimize f20 by changing these two cells, make them non-negative, so they have to be greater than 0. All these smoothing parameters are between 0 and 1. So let's add a constraint that these cells are less than or equal to 1. Okay, so you see here the mean absolute deviation is 26 million. Solve. It's now 14 million. And kind of interestingly here is our alpha is 1, so we're always updating the level pretty much from the previous tonnage, from the current tonnage, but we're updating the trend a little bit more slowly. Now, some of this is we've got this extreme value. I would think if we kept all of the, because we only have a small number of years, if we kept like 40 or 50 years, I'm sure we wouldn't have got that extreme value. So the level is almost completely adapting to the latest value, but the trend is updating a little bit more slowly. So let's, so again, and I'm doing this because in reality, this is how we tune these models, is we basically have past data. We do this kind of one ahead forecasting, calculate the error, and we set our parameters to minimize the error on the current data. And in fact, sometimes I would, if we had more data, I would say I only would calculate the mean absolute error maybe after period 5, after we have what we call sufficient burn-in. But I wanted to stick exactly as the book data, and we only have like 10 periods here. So the last thing we need to do to make this the same as the book, let's just select total tons and select the forecast, and let's do an insert, and let's do a line graph, and I'll call this double exponential smoothing or Holt's method. And you can see how close the forecast is to the actual. You know, we have the trend here. Our forecasts are almost, we've got this kind of pretty fixed trend here. Our forecasts have just latched onto it and are really, really good. But of course, they didn't. We suddenly had a drop in coal production, so this type of forecasting couldn't fix that. But overall, and you see that our forecasts only start in period 3, but overall doing pretty well. Let's just add some axes. Axis total thing is year. And this is the tons of coal production. So I'll just call it tons of coal. And there we have it. That is the book example for the double exponential smoothing, or what's often called Holt's method. I pretty much followed the book example as is. Just be aware the equations. I don't like the notation in this book because you have F for the forecast and also F for the current value, which just almost makes it very hard to interpret the equations. When it comes to the exam, I'm not going to ask on the equations. I'm just going to know that you can interpret the parameters and interpret the output. But do be aware the free forecasting book I linked to in my initial video, this has a much better explanation than this textbook. Okay, so this is the book example, but with additional optimization of parameters.